Before we get started on propagation of uncertainties, just to go over some key terms. Absolute uncertainty is just the plus or minus value, but that's when you're adding and minusing with your calculations. And for percentage uncertainty, when you're timesing and dividing, so you need to add percentage uncertainty. So we'll go through that in a second. So just basically just an overview. So when you're propagating uncertainty, always go for the largest error and just apply that to all of your values. As I said before, when you're doing your calculations, and you're adding and subtracting, you add the absolute uncertainties. And when you're multiplying and dividing, you add the percentage uncertainty. So this is not very big in tests, but this is very big in your internal assessment. So I'm going to set it out as an internal assessment and use an actual internal assessment to show you how to do it properly. So the final uncertainty is a significant figure, and the final answer is rounded off to a similar number of places as the final uncertainty. So looking at this one here, this one here is, if I just show you what the actual, the original table looks like. So this is the original table. You can see there's some very large percentage differences, which I'm going to keep, but realistically you would have removed them. And at the end I'll show you what the graph looks like when you've done it properly, which I'm not going to do. I'm going to leave them in there, but when I've removed them, it kind of looks like that. And so that's the table that I would want to see. Okay, so just going over this, I'm going to leave them in there. So this experiment was 20 mils of sulfuric acid, 20 mils of carbonate, various concentrations, using a video so you could get some very good uncertainty on the timings, and then measuring the volume, I think through a syringe. And so when you put something in there and you have to close it, you're going to lose volume straight away. So it's kind of a little bit unreliable at the very start. And you can see from the percentage differences that there's huge amounts of error in those. But I'll leave them in here, and you'll see what the difference is if you don't get rid of them. So the point of that being is to do something called a percent difference. It's taken from the physicists. It's basically just getting the average and minusing each value by the average and then dividing it by the average. And their general rule of thumb is anything that's greater than 20% difference is anomalous. So instead of just umming and ahhing about it, you have a very objective way to determine whether you're going to allow something or not. Now, the data could be quite strange, so maybe a 5% difference might be significant, or maybe it's 80%. In this case, I've gone for the 20, which is the rule of thumb. Now, the other thing to do is, because they're student experiments, usually the random error is much greater than the instrument error. And so we do an absolute uncertainty of the mean. So it is nice to do a repetition of 5, not just range 5 repetition of 3, but range 5 repetition of 5. But that is quite fine for this experiment. It still works well. It would have worked a lot better with 5 trials though. And so what you do basically is, this is going to be uncertainty propagation, but we have to work out where it is. And so basically you try and get one clear, concise table with all your raw values and calculations like here. I've just taken out this one here because that's the one I'm going to focus on. Always focus on the one that's worst, and the worst one was 83%. When I fix the data, I actually have to redo all my graphs and tables and values all over again, because once I've removed all the greater than 20% difference anomalous results, it comes down to just a 0.31, which is much, much better. And so I have to redo everything, and I'm not using this value at all for my example calculations. Okay, so just take a very systematic approach. Just start from the left-hand side and work your way all across to the right-hand side. And then also just put 2 simple lines, like I showed here, one for calculations, and then match them parallel with the uncertainty, so it's easy to find. So you can just systematically go through it. It's easy to read and easy to understand. So the first one here is, I like students to first take into account if there are any errors inherent before you start. So some of the stock bottles have 5 or 10% errors on them, and so when they're weighing a certain mass, there's a 5 or 10% error straight away. The error won't be in the weighing because the technician uses a very accurate balance. And generally the errors won't be very significant either with the solutions, because factors of 3 don't matter, and they're using very huge volumes, like a 2 litre volumetric flask, which would have even smaller error. So generally the errors don't exist when the technician gives you things, but they could exist for masses. So you just have a quick check. I have a database of pictures of the stock chemicals for my students. This one's a 1% error that I would throw in there, but the nature of this experiment, it's heterogeneous and it's not mixing properly anyway, and it's in excess, large excess. So in this case, I just write this down, that I've taken a good understanding that there's no uncertainty with the chemicals that I start with. Moving on to the next thing. So doing an average, averages have the same uncertainty as what the individual values have. And so that's not a big deal. But then you always do 2 things. You do your instrument uncertainty, then you do your absolute uncertainty of the mean. And you always work with whichever's larger, and it's almost always the absolute uncertainty of the mean. And so we're working with that. That one's quite large, 0.8. As I said, when you get rid of your anomalous results, it's actually only 0.3 and everything works out quite fine. But we're working with this one and leaving the mistake in there. Okay, so going on from there, just give one example of how percent difference works. And so I've got that there. So one example calculation for everything that's done. So even if it's an average or a percent difference, you still put it in there. This will end up being part of our uncertainty propagation. Okay, so also show them quite clearly how you worked it out. So do a proper graphs for this. Mark out where the delta y and delta x are so that they can read these values here. So is it 2 and then 1.3 or whatever, and they can compare it to make sure that you've done the right thing, which is over here, 2 and 1.3. So they can follow it. So everything's clear, 0.8. Okay, so now we're getting into the final calculation, which is the rate. So it's a volume over time. And so we have here, this is the example one that we're using because this one has the worst values. And so those values are read from the graph. And so there's your calculation. We have 2 minuses and a divide. And so the two minuses, we're adding absolute uncertainties that we have. Either we worked out this one, it was better, the larger error was the absolute uncertainty in the mean, and this one, the larger error was the instrument uncertainty. And so there we get our new absolute uncertainties. The thing is now we're dividing, so we have to grab the absolute percentage uncertainty. So we have to grab the absolute and divide it by the total in both cases. So they're 94%, 30%, 94% and 3% are the percentage uncertainties. So now we add those percentage uncertainties. So we have a 97% uncertainty that we're carrying through. So now that we have our final results, 2.43, 97% of that is 2.4. So always to 1 sig fig, so it's plus or minus 2. And round the final answer off to the same number of unit placings as the error. So technically this should be 2 plus or minus 2. So when you get rid of the percent uncertainties, it's 0.6. So 2.0 plus or minus 0.6 is a much better thing to work with, and that's it. That's it's not that easy. It's a hell of a lot of work, but it looks clear and easy quite here hopefully, but it takes a lot of work to get to that. So the final graph you can see is quite bad. You could even have a rate order of 0. It could be within the error bars, but the R squared is much better if you do a first order. And then if you do fix it, it does end up looking like this, 0.97, rounds off to 0.98, so that's getting really, really good. That was a point, I think it's actually a 0.6 if I do it properly. And so you can see that's quite a significant difference between these two if you've removed the anomalous results through percent difference.